Okay, we'll get started. So, welcome to this class ECE 7202, and this is also cross-listed with Industrial Engineering Department. So, if you are an Industrial Engineering student, you can sign up for ISE 7202, or if you are okay with ECE 7202, it doesn't matter. You can register for any class. This class will be running on Tuesdays and Thursdays, so 11:10 to 12:30 p.m. I'm sure you're all aware. The classes will go all the way until December 10th. I'll be your instructor. My name is Abhishek Gupta. I'm an associate professor in the ECE department. So in alternate years, sometimes ISE faculty will teach this class. Sometimes an ECE faculty will teach this class. So this year, I'm an ECE faculty and I'll be teaching this class. My office is 464 Dries Lab, and the office hours will be Thursday 1 to 2 p.m. right after the class in my office. You can check my calendar. So my calendar link is on Carbon. So you can definitely check my calendar, send me an invite for a time that is suitable for you to meet me in case the office hours does not work. So this course is about reinforcement learning. Of course, generative AI has been a fairly important topic in the recent time, so we'll be covering a little bit of generative AI towards the end of the course. But the course is mainly about reinforcement learning. Reinforcement learning is one of the important technology for many products and services that you might be using on a daily basis. How many of you shop from Amazon? Many? So Amazon's recommendation system uses reinforcement learning. One of my ex-PhD student actually worked at Amazon as an intern, and where he devised reinforcement learning based recommendation systems for Amazon. How many of you use Netflix or Amazon Prime or whatever, some sort of video streaming platform? So again, recommendation systems there uses reinforcement learning. If you're using I don't know whether this building air conditioning system is using reinforcement learning or not, but you're using data centers. I mean, you're not a direct user of data center, but you are using services which are hosted in data centers. So they also use reinforcement learning for energy optimization. If you're using hybrid vehicles, or if you're using electric vehicles, and assuming it is a modern electric vehicle, some of the processes internally within the electric vehicle will be using reinforcement learning for some sort of optimization. So where reinforcement learning is useful, when you have a lot of data but you don't have a system model. So if you think about it from a recommendation systems perspective, we are the users of recommendation system, and our data is what all items we have purchased in the past. So that's the data set that is getting generated. But there's no model of the brain, of my brain or your brain or somebody else's brain, that will help Amazon figure out that these are the items that this particular person is going to buy in the future. So that's the case where you have a lot of data, very rich amount of data logged, but you don't really have a model for the system, and therefore reinforcement learning becomes a very valuable tool to figure out, to optimize what should be served to the user. Okay. In modern days, large language models are using reinforcement learning for coming up with more relevant response to the prompt that is generated by the user. Agentic AI has been using reinforcement learning. Payment systems is another area where I have personally advised companies on using reinforcement learning for optimizing the payment success rate. Drug discovery is another area where people are toying with the idea of reinforcement learning, but I'm really not sure whether it has been successful or not. Can you please pass it on to him? Thank you. So a lot of different areas where reinforcement learning either has been used and you're already a user of it, or people are looking into it and hopefully will be users of it 5, 10, 15, 20 years down the line. Anybody from biomedical/bioinformatics department? Okay, one person. Okay, perfect. So in this particular course, so this is, the prerequisites are of course grad standing in engineering or math or physical sciences. However, so we don't have a prerequisite of probability and optimization because people from diverse background are coming in. So when we make a prerequisite, it means that the student must have taken that particular course. Otherwise, the student is not allowed to sit in this particular class. So there are no prerequisites for this class, but that doesn't mean that you do not need to have prior knowledge of probability or optimization to sit in the class. So if you haven't taken probability or optimization before, this class is going to be very, very difficult for you. So I just want to make sure that you understand that. And that's why I uploaded assignment 1. It's on Carbon. So you can take a look at it. If you are finding it difficult to do the assignment, I would encourage you to drop this class. On the other hand, if you want to learn the prerequisite within this week or over the long weekend, then I have given the list of topics that are important in order to understand the contents of this course. So the first most important topic is linear algebra. You have to have a very good and strong working knowledge of linear algebra, which is matrix multiplication, eigenvalues, matrix inverse, and so on and so forth. The second most important topic is dynamic programming, maximum principal, gradient descent algorithms, and linear programming. Much of this topic is studied in ECE 5500. So I will be teaching ECE 5500 this semester, and that runs Monday, Wednesday, and Friday. So tomorrow will be the first class for ECE 5500. So if you are interested in optimization and optimization algorithms, I encourage you to enroll for ECE 5500. However, much of the stuff that we talk about in ECE 5500 towards the later part of the course, where we talk about dynamic programming and so on, that's a prerequisite for this particular class. So you need to know dynamic programming. We'll cover all of it in the classroom in the first 2-3 lectures, but you have to have a working knowledge and you have to be very comfortable with dynamic programming to be able to understand the contents of this class. And then the third prerequisite is convergence of random variables, weak and strong law of large numbers, central limit theorem, and Markov chains. Again, there are online resources where you can get information about these topics. We'll cover a lot of these prerequisites in the class as and when needed. However, you have to have a working knowledge of these things, or you should be able to pick up a book and read up about these things on your own. And what is actually needed to succeed in this particular class is mathematical maturity. So there is no way to define what a mathematical maturity is, but you should be able to understand the proofs. You should be able to derive results completely on your own, and you should be very familiar with mathematical reasoning. So that's the important part, and that's what I'm expecting as part of the prerequisite. So in many cases, this mathematical maturity comes because you have taken a lot of other courses in engineering or math or physical sciences department. We don't really have a course text. Unfortunately, I don't like any of the books written on reinforcement learning. They leave out many important topics. So there are no course text. However, I'm going to cover sections from neurodynamic programming, which is written by Bertsekas, and some other books that are available for free. And I'll be uploading some of the links to these books on Carmen, so that way you will have access to those books as and when is needed. We'll also be covering some topics from research papers, so not everything is in the form of a book or textbook. So there will be research paper used in the class as well. I have provided a list of topics that we'll be covering in this class. So we'll start with reinforcement learning. We'll spend quite a bit of time on understanding the concept of state, and this is the part that actually gets left out in most reinforcement learning books. So all the book starts with knowing what the state of the problem is, but the real problem that I feel in many real world situation is we don't even know what the state of the system looks like. So I want to start with the concept of state. This concept was proposed back in 1950s, and it was there in the books of 1950s, but then it got out of the books 1970s onwards. But I want to go back to 1950s, review what they have done, what they thought was the state of the system, and then look into the modern problems and figure out what the concept of state is. We'll cover algorithms for solving MDPs. Then we'll talk about policy gradient theorems, reinforcement learning algorithms for finite state, finite action MDPs. Then we'll talk about stochastic approximation theory and convergence of asynchronous algorithms. We'll then move on to MDPs with continuous state, continuous action space. That's my favorite topic. That's what my research is about. We'll get into MDPs with continuous state, continuous action probably by early to mid October, after which things will become very difficult and challenging. We'll talk about complexity theory for MDPs, approximate dynamic programming, universal function approximators, and some universal function approximation theorems. And then we'll talk about value iteration, fitted value iteration, deep reinforcement learning, inverse reinforcement learning, and then applications of reinforcement learning to generative AI systems. The evaluation policy would be simple and straightforward. There is 4 homeworks and 1 research project. The homeworks are somewhat involved because I want you to spend some time thinking about the theory and some time writing codes for reinforcement learning. For the coding part, you are allowed to use AI tools like Claude or OpenAI to generate some sample code on which then you can edit and solve the assignment. One of the things that you will learn is troubleshooting AI generated code is far more difficult than writing the code completely on your own. So certainly you can choose to use Claude or AI tools to generate the boilerplate code, but I will warn you that it might take you more time to troubleshoot that code than writing it completely on your own. But it's completely up to you. I'm not going to stop you from doing using AI generated code. But on the theory side of the questions, assignments, you have to do it on your own. You cannot use AI tools to solve the theory problems. And frankly speaking, I don't know whether AI tools will be able to solve the theory problems or not. I haven't checked myself and I'm not going to check it, but I would encourage you to use your own skill set to solve the theory problems. And the homeworks, you can write it on an iPad or you can write it on a sheet of paper. You can submit the homework in class. Alternatively, you can, if you're writing it on iPad or something, you can upload the PDF on Carmen, and then all the grades will go to Carmen. Like I'll be grading everything on Carmen. So that will make things easier. You cannot copy someone else's homework, but you can work in a group. That's completely fine as long as you write up your own solution. Research project. I don't think I have given you. I haven't given you a list of topics that you can pick up for research project, but research project is something personal to each student. So if you are a student in bioinformatics, you probably want to pick up a research problem that is within that area of bioinformatics. And what I'm expecting you to do by the end of this semester, you should have studied the problem, you should have created a presentation, you might have written a bunch of code to solve the problem. So you will have to present that in the class. So I think December, we have about 1.5 weeks in December, 1.5 weeks of classes. So those 3 classes in December, we'll probably be going through the presentations, class presentations. So whatever you have done will be presented in the class in front of the rest of the class. There'll be question and answer. So and then the presentations will be uploaded on Carmen in order for me to evaluate your work. There are no classes on October 16, which is the autumn break, November 11, which is a Veterans Day, and Thursday, November 27, which is Thanksgiving. There'll be a few days when I'll be out for a conference or something, so those classes will also get cancelled. I'll let you know when those time comes. And then there are other statements about counseling services, health and safety requirements, Title IX statement, and so on and so forth. You can go through it in your leisure time. Has everyone received this course information sheet? Anyone who has not received it? Awesome. One additional note, if any of you are interested in entrepreneurship and want to start a company, there is a VC called Radical Ventures based out of Toronto, and they are looking for people for their master class. So if you're interested, let me know and send you the resources in order to apply for that masterclass. They are a very well-known and established VC firm who are funding a lot of AI-based companies. So if you're interested, do let me know. Okay. Any questions so far before I move on to the technical topic? Did you receive this? Did you receive this? No? Perfect. Okay, so let's go into the core of probability theory. So let's cover a little bit about probability theory. So omega is set of all uncertainties set of all events, which is basically subsets of omega. And P is a probability measure. Okay, has anyone seen this omega FP definition of probability? Some people? Okay. Okay, so omega is set of all uncertainties. So let's think about it. How many of you know, how many items does Kroger keep in their store? Anybody knows? They have 13,000 unique SKUs in each store, so 13,000 items. So each item, like the set of uncertainties could be item and then the number of items that they have. So it would be, that's the set of, so that's the total. So you will have item, comma, quantity pairs, and you can have maybe like 20 or 30 is the maximum quantity that they might have for each individual item. So you can imagine this matrix of 13,000 items as rows and the number of items as columns, and that's the set of all uncertainties in the case of just looking at Kroger, right? So depending on what situation you might be in, the set of uncertainties will be very different. In the case of Amazon, how many items does Amazon has? How many listings does Amazon has? Maybe 1 million? I don't know, like I'm just making up the number, but probably 1 million items, right? And then they might have certain quantities. So in the case of Amazon, the set of all uncertainties would be items multiplied by their inventory numbers, potential inventory numbers. So that's the set of all uncertainties. If you look at individuals who are buying things on Amazon, right? So we buy things in a sequential manner. So what's the set of uncertainties there? I'm going to buy item 1, and then I'm going to wait for X number of days, and then I'm going to buy item 2, and then I'm going to wait for Y number of days, and then I'm going to buy item 3, and so on and so forth. So the set of uncertainties in the context of a person who's buying stuff from Amazon is going to be very, very large. Okay? So the cardinality of omega could be very different depending on the number of items, the quantity, the time series, and so on and so forth. Okay? So F is the set of all events or measurable subsets of omega. Okay? So we all know what a subset of omega means. I think some of you may know what a measurable subset of omega means, especially those of you who have taken real analysis. Uh, so let's think a little bit about what does it mean for something to be measurable. So can we measure, so what is measurable in our day-to-day life? Can I measure the length of this blackboard? I think we can get an inch tape and we can measure it. Can we measure the happiness in our life? Is there an inch tape or is there something that we can use to measure the happiness level of each other? We can't, right? Can we measure the area, the surface area of this blackboard or the surface area of this room or the volume of this room, right? The answer to those questions is yes, there are certain things that are measurable and certain things that are not measurable. Okay, so in the case of, so let's say my omega was R and my subset A, which is in F, so let's say A is equal to 0, 1, then I can measure the length of 0, 1, which is equal to 1. Alternatively, my A could be open interval 0, 1, and my length of open interval 0, 1 would also be equal to 1. Right? So depending on what my set A looks like, I can measure the length. In the case of omega being Rn, so let's consider the case of R2 and let's consider A to be 0, 2 cross 0, 5. So that's my set A. It's a subset of omega. So for this, we need to keep the measure as the area because it's a two-dimensional space. So the length, you can have a length and you can have a breadth, and therefore we need to have area as our measure. So area of A is going to be 2 cross 5 equals to 10. Okay, so we have set of all uncertainties, then I'm taking a subset of that set and I'm going to put a measure on that particular subset. So in the case of real line, my measure is going to be length. In the case of two-dimensional space, my measure is going to be area. In the case of three-dimensional space or multi-dimensional spaces, my measure is going to be volume, right? But we can pick any other measure, right? So these are not the only measures to pick. We can come up with our own set of measures that we can use to measure, have an inch tape for that particular subset of omega. Okay? But that measure has to satisfy certain properties. So I'm not going to go into the measure theory and figure out what those properties are going to be, but I will talk to you about what the probability measure should satisfy in a bit. Any questions so far? Okay. So how do we construct this set of all events or measurable subsets of omega? So let me give you a very simple way to come up with this subset of omega. For the case of real line and this R square and so on, but in general there is a whole abstract theory of measure theory which talks about it, so we'll not get into that. But just to give you an idea and just to give you a feel for what this means, I'll tell you how exactly the measurable subsets of R is created. So let's define F0 as the set of all open/closed intervals. Okay, set of all open and closed intervals of omega of R. Then I'm going to pick F1 as the set of all countable intersections or unions of sets in F0. Okay, so let me give you an example. So I have AK equals to AK BK, that's the interval. So that's part of, this is in F naught. Now let's define a set B equals to union K equals to 1 to infinity AK, C equals to intersection K equals 1 to infinity AK. So these AKs are in F naught. The set B and C will be in F1. Okay, this is the set of all countable intersections or unions of sets in F naught. And I can keep going down the rabbit hole. I can define F2 as the same thing, F1 and F3 as the same thing for sets in F2 and so on, and I will get to F infinity minus 1. Okay, and this set of all measurable subsets are going to be equivalent to F infinity. Yes, please.
I don't really understand. So B stands for all the open interval of AK, right?
That's right. So all of these intervals. So this is a closed interval, but you can have open intervals as well, and that's part of F naught. So F naught is set of all open / closed intervals of R.
Okay. So C is like which one is closed and which one is open?
Sorry, can you say that again?
C, which one is equal to which?
B and C?
Yes.
This one will be part of F1. So B and C is part of F1. It's not part of F0.
Oh, okay.
Right? Yeah.
I have a question.
Yes, please.
Well, what's your definition of AK and BK? The lowercase.
I mean, you can pick whatever AK and BK you want. So, okay, so let me give you an example. My AK is 1 over K, 1 minus 1 over K.
And so C as your definition is, so C, since C is the intersection of
Intersection of all AKs.
So it must be a closed interval as well. So but B can
It's not really required. So if each of my AKs are 0, 1, then C will also be 0, 1.
So I just want C is also closed, but B can be some.
That's right. It could be a bunch of intervals together, right? So B could be something like 0, 1 union 2, 3. What's the length of 0, 1 union 2, 3? It's 2, right? So one length of this is 1, length of this is 1, so it's 2. So I can measure. So it's a union of two closed set, and I can measure the length of B, right? So B is a measurable set, even though it's not an interval, right? So it's not an interval, but it's still a measurable set. And I can keep going on and on, keep constructing new types of sets, and at the end I'm going to get F infinity, and F infinity is the set of all measurable subsets of omega. So I can measure the length of this, 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 and so on and so forth. So I can measure the length of all sets that are in F infinity. And the funny thing is, or the interesting thing is, that there are subsets of R that are not part of F infinity. We'll not study those subsets in this class, but there's this whole area of mathematics called real analysis, which talks about that in the entire 40 lectures in the class. So we'll stop the discussion right here about measurable subsets, but if you're more interested in this, please do go and take real analysis, where this subject is taught in more details. Any questions so far on measurable subset? Okay. You can do the same thing for R2, you can do the same thing for R3, R5, R10, R500, and so on. Okay, so F is the set of all events or subsets of omega. These are known as measurable subsets because you can measure the appropriate quantities for these particular subsets. And then let's talk about probability measure.
I just have a
Yes.
the measure is a mapping, and the map is always mapping to a real number, right?
That's right. It's always mapping to the real
Cannot,
number.
the map cannot be R squared, but the left side of the mapping can be R squared. Okay?
That's right.
But the right side must
Correct.
be a real.
Absolutely,
Okay.
absolutely. In fact, you can also have omega, which is just a number, so you don't even have to have real line. It could be just 1, 2, 3, 4, 5, 6, 7, 8, and so on. It could be set of all integers. It could be set of integers cross integers, and so on and so forth. But the rest of the stuff goes through, except that the notion of open and closed interval is not there in the case of integers and natural numbers. Yes, please.
So what measure to choose, does it depend on the application? Like
It definitely depends on the application. Yeah. Okay, so what does probability measure mean? So probability measure is a mapping that maps the set of all measurable subsets to something between 0 and 1. So it can't be negative. So probability measure cannot take a negative value. And it's always upper bounded by 1. So what are the different axioms this must satisfy? So the first is probability of null set. So this is my null set or empty set must be 0. Probability of omega must be equal to 1. And the third one is the most important restriction on the set of probability measure. I mean, it's a restriction on all measures, not just probability measures. So if ak k equals 1 to infinity are disjoint, then probability of union of ak is equal to sum of probability of ak. So if you pick a sequence of disjoint subsets of omega, these are all measurable subsets of omega. So I can measure it. I can measure certain quantities. So if I take the union of all these disjoint sets and I want to take the measure, it's actually summation of the measure of individual sets. Any questions so far? How many of you have seen this definition of probability? How many of you have not seen this definition of probability before? Okay, few people. Okay. So something to think about, something to review when you go back from this lecture, because again, these are the important fundamentals that are needed to understand reinforcement learning. Okay, so we learnt about the probability measure. Now let's talk about random variables. So random variable is x. It's a map X from omega. Let me put it R for now, but it could be Rn, in which case it's called a random vector. Or let me just write it. So variables when it's a single dimensional, vector when it's multidimensional object. So I have the set of all uncertainties and I'm going to map it to a real number, and that gives me a random variable. Okay, just let's look at an example. So we just talked about Kroger, right? So Kroger has 13,000 items, and there will be X number of item, XK number of item for each K item that they might have in the store. How can we generate a random variable out of it? So let's look at the price of the entire inventory in a Kroger store, right? So each item has an associated price, and there is X number of items. So you multiply the price by the number of items, you add it all up, that gives you the total cost of inventory at Kroger, right? So that's a random variable because it's a real number. Price, the total inventory cost is a real number, right? And we can use the information of the inventory to come up with that particular number. What about total number of items in Kroger? So you have 5 milk bottles, 2 cheese strings, and so on and so forth. You add all that up, you get another random variable. What about random vector? So let's say we are only interested in the quantities of items. So then we get a random vector because you have 13,000 items. So this n is going to be 13,000, and I'm going to map omega to Rn, and I'm going to get 13,000 dimensional vector, which will give me the total number of items. Total number of, so each, what's the number of each item in the store? So that gives me a random vector. Okay. So you have the set of uncertainties. It's a very, very abstract set. It has a lot of stuff in it, but sometimes we are not interested in the entire stuff. We are just interested in some real number or some vector that are associated with that uncertainty. So that's what is studied under the umbrella of random variables or random vector. So the thing I want you to have in mind is, here is my set omega. I map it to a real number. That gives me a random variable. So random variable is a map. And sometimes it's interesting or important to go from the real line back to the set omega. And so you will have like a subset A here of real line. And you do an inverse map, and you might get a subset like this in omega. So we have defined the probability measure on omega. I want to get a probability measure on x. So the way to define that is as follows. So probability of x is in the set A. Subset A there is probability omega is in x inverse A. So this is my x inverse A set. Okay, so this is the set of all inventory in Kroger. I am looking at the total cost of the entire inventory in Kroger. So that's my x, that's my random variable. I get something which is a real number. I look at a subset of real numbers. So let's say the inventory is between $10 million and $11 million. So this is my 10 million, This is my 11 million. So that's my interval A. So now I have to figure out what are the possibilities which is going to give me. So each inventory figure here is going to give me a number between 10 to 11 million dollars, right? So I'm going to get this X inverse A set, which means that the total price of inventory within this set is between 10 to 11 million dollars. And now I will look at the probability measure over this particular set. That's going to give me a probability measure over the random variable X. Okay? So that's a way to transform a probability measure into one space to a probability measure into another space. So this probability measure is over the set of random variables. This probability measure is the original probability measure we started with, which is the set of all uncertainties. Yes, please.
Is that called the push forward measure?
That's true. It is.
So,
Yeah.
is inverse X always inverse X mapping always exist?
Right. So there is something called invertible functions that you study in undergrad class. So this is what is called a generalized inverse. So the inverse mapping will always exist. So for any the theorem is if you have a measurable map, the inverse is also measurable. So, but we are again not going into the stuff in real analysis. But if you have already taken that class, then that is true. The inverse will always exist. Any other question? Okay. So we have talked about probability measures. We have talked about random variables and random vectors. Let's talk about independence and conditional measure. No questions? Okay. Right, independence. So I have two random variables, x1 and x2. They map omega to R. And we say that x1 and x2 are independent if and only if probability of x1 in A1, x2 in A2 is equal to probability x1 in A times probability x1 in A1, x2 in A2. So this is the same as x1, x2 is in A1 cross A2. So sometimes people write it as this, sometimes people write it as this. They are the same thing. A1 and A2 are measurable sets. And this is the definition of independence of two random variables. Let's talk about the following. Let's omega be the inventory at Kroger, so that's the set of all uncertainty, cross the weather, what the temperature outside is. I look at the temperature as one random variable, and the other random variable is the inventory level at Kroger. Do you think they are independent or dependent? Do you think that the temperature, the outside temperature, is independent of Kroger's inventory, or there is some sort of dependence between them? Dependence? Why is it dependent?
Well,
what they have is based on who buys what, and people go out less if it's cold, and
That's
also
right.
trucks.
Right, right. So our consumption, as people, our consumption is pretty seasonal. So in the summer, we'll have more cold beverages. In the winter, we'll have more hot beverages. So Kroger is going to stock items according to the people's preferences. And therefore, they are no longer. So you might think that what does weather has to do with Kroger's inventory, but unfortunately, the way we behave, it couples the two random variables, outside weather with Kroger's inventory. Now let's change the definition of omega. So my definition of omega is temperature on Mars, some point on Mars, cross the inventory at Kroger. Are they independent or are they dependent? Do you think we consume according to what the temperature on Mars is? We don't really care, right? We don't care, therefore they are independent random variables. What about the inventory of Kroger and the data center energy usage? Are they dependent or independent? It sounds independent. What does data center have to do with Kroger? But you really have to look at the data to figure out whether they are actually independent or not. I really don't know the answer, but I'm just throwing it out as a food for thought. So when you look at two random variables, it's not obvious whether they are independent or, I mean, sometimes it is obvious, as we argued in this class. Sometimes it is non-obvious. In fact, there are many memes. I know nowadays everybody looks at memes. So there are memes which says that the number of shark attacks is correlated with, I don't know, something else, I don't remember what that meme was, but sometimes people find these correlations between two seemingly independent events. But sometimes there is a strong correlation and it's not very clear why there is a correlation between those two random variables. But anyways, this is the definition of independence, and many a times we will stick to this particular definition. I mean, not just we, but everyone sticks to this definition of independence. But when you are in a real world scenario, when you become a data scientist at Amazon, and you have to you're looking at the Amazon grocery vertical and the weather of Columbus or weather of whatever, the rest of the United States, you will have to do some data-driven analysis to figure out whether they are independent or not independent. It's not, most of the time it's not obvious when you are in a real world setting. Another food for thought, this is the temperature, this is the movies that people are watching on Netflix. I'm not sure whether there is dependence or independence, but if you are a Netflix data scientist, you better know whether they are independent or dependent, and you have to look at the past data to figure out the independent/dependent structure between the two random variables. Okay. So then that brings us to the definition of conditional probability. Okay, so conditional probability. What does conditional probability mean? Given that I know I have some knowledge of x2, how can we come up with a probability over what x1 looks like? Okay, so let's look at an example. So right now the outside temperature is 64 degrees Fahrenheit. What's the probability that there are 10 1-gallon milk cartons at Kroger at this point of time? That's a conditional probability. I can observe the temperature outside, so that's my x2. I know what value of x2 is, and I want to know what's the probability of certain event is based on my knowledge that I already have. That's conditional probability. So x2 is given, and I want to know what's the confidence on x1 looks like. How many of you have seen conditional probability before? Many people? Okay, wonderful. The last thing that I want to talk about is expected value, which is given by so typically you will either have integral or you will have summation depending on whether it's countable or uncountable. But the expected value is the random variable multiplied by the probability of that random variable appearing. And then you add it all up. Okay, so it's an average of all the potential random variables you are going to see about that particular uncertainty. Any questions on this? Yes, please.
So in the integral form,
Yeah, it'll look something like this. Integral of x omega p d omega. This integral is over all omega. So p d omega is the measure. Let me write it as this form. Omega plus d omega. So that's p d omega. So you're looking at this interval, and you're looking at the measure over that, and then you multiply it by x of omega, and you take the integral over the entire set. Okay. Any other question? Okay. So expected value. What's the expected inventory level at Kroger? So you look at the past 1 year of Kroger data, you look at the inventory cost on a daily basis, you add it all up, take the average, that gives you the expected value of inventory of Kroger over an entire year. That could be, I don't know what the number should be, but probably like maybe $15 million. That's the total inventory, average inventory of Kroger over an entire year duration. Okay, so we are done with the entire stuff I wanted to cover about probability theory. Any questions on this? This is the stuff that I expect you all to know. If you don't know, please go back and review it from an appropriate reference. Wonderful. Let's talk about dynamic decision process. So in dynamic decision process, there is some activity going on. You are observing that particular activity, and on that basis, you are actually taking some action. And then that action changes the nature of observations you are going to make at the next time step. And this crucial fact, that the fact that your action now is going to affect the future state of the system or future observation, is what makes it dynamic. If it were not affecting, if your action was not affecting that particular quantity that you are observing, it's no longer a dynamic decision process. So if I increase the thermostat of this room, or increase the temperature of the thermostat of this particular room, then of course the temperature of this room is going to rise. Alternatively, if I increase the air conditioning, the temperature is going to go down. Right? So it's a dynamic decision process to control the temperature of this particular room. But if I increase the thermostat up or down here, it's not going to change the temperature on moon. Right? So my observations about moon's temperature is independent, completely independent of what I'm doing here on this planet. Therefore, it's no longer a dynamic decision process. Right? So what happens in dynamic decision process is we make an observation, then we act, then we observe again, then we act again, and this thing goes on and on forever. Many a times when we are acting, we also incur a cost. Every time we act, we incur a cost. So then we are observing not just the quantity, but we are also observing the cost. Okay? So we observe, we act, we observe a cost, and then we make the next observation, then we act, we observe a cost, then we do the next observation, and so on. So this process goes on and on forever. I mean, not forever, but for whatever. Depending on the situation, it might last for a few minutes, days, weeks, months, or years. So let's look at an example of this infinite, not infinite, but whatever. So this sequence that arises. So anybody knows when was this building commissioned? Journalism building? No? So this building was first commissioned on July 17, 1924. Okay? So that's about 101 years ago this building was created. I mean, of course, it went through many renovations since then. It's not like maybe the foundation is still from 1924, but the air conditioning system is certainly not from 1924. Okay, so since 1924, the temperature of this room is changing. Okay, so in 1924, on July 17, there was certain temperature of this room. The air conditioning system acted upon it. The temperature changed. The temperature of the room changed. So the air conditioning system sensed what the temperature is, and then it acted upon it, and so on and so forth. This thing has been carried out for the last 101 years for this particular room or for this particular building. Okay, let's talk about data center. Okay, so data centers, one of the important things in data centers is as people are watching Netflix and as people are requesting YouTube videos or New York Times news articles or university library articles and so on, that is the load on the data center. In order to service that load, computers have to do some processing. In order to process, it generates some heat, and then there is an air conditioning system within a data center that has to expel that heat into the outside environment. So the air conditioning system observes the temperature inside the data center. It turns on and off whatever the air conditioning, like the amount of cold air that needs to be injected into the data center. It observes the cost of injecting or creating that much amount of cold air. Then it makes the observation at the next time step. You have a completely different load. So I don't know how many of you are aware, I'm sure you can relate to it. So the Netflix load is very flat throughout the day, and at 5 p.m. or 6 p.m. the load peaks. And why does the load peak? Is it news to us that the load peaks at 6 p.m.? Not really, because all of us will go back home and we'll start cooking, and then we'll turn up Netflix, we'll start watching some show, and we'll cook and eat our dinner while watching Netflix, right? So the load that is on the data center that is servicing that Netflix load is actually quite different from one time to another. So different times will have different observation about how much compute load is coming, and then the air conditioning system has to act accordingly in order to incur the cost. And what should the goal of the air conditioning system of a data center be? It should be to minimize the total energy consumption of that data center. So it needs to figure out how to schedule the cooling of the data center so that the temperature is within a specific bound. So typically for data centers, the temperature has to be between 70 to 75 degrees Fahrenheit, and to make sure that the total cost of servicing that particular load is minimized. So if you are servicing a university load, right? So a lot of the people are actually accessing their university systems during the day. So a data center that is servicing the university load is going to see quite a different demand pattern in comparison to a data center that is servicing the Netflix load. Okay. What about healthcare? A doctor is observing your health parameters, your blood test results, your MRI, CT scan, whatever. It gives you some drugs, suggests some treatment plan for you. There is some cost that is incurred. You might have a headache, you might have stomach problems, stomach pain, whatever, right? So incurs the cost. The doctor makes that observation and then changes the dosage of the drug, changes the dosage, the treatment plan, and then incurs the cost and so on and so forth, right? So the doctor is also going through a dynamic decision process on a day-to-day basis. Selling items on Craigslist. So I'm a big Craigslist fan. I sell and buy items on Craigslist all the time. So I'm observing a post. There is a price that is given for a specific item, and I can decide whether or not I want to buy that item, right? And then a cost is incurred, and then I can make the decision, further decision about whether to buy something else or to stop the buying process completely. If you are a Netflix engineer and you have to decide a recommendation system, you're going to observe what you as a person are watching, or whatever you have watched so far, like what all movies have you watched so far. It's going to recommend a new set of movies for you. It's going to see whether you clicked on the movie or not, whether you watched the movie or not. Did you watch it for 2 minutes? Did you watch it for 2 hours? Did you do a binge watching back to back for that particular recommendation that I served to you? Based on that, my new observation will get created, and then I'm going to send you a new set of recommendations next time when you log into Netflix. And then again, I'm going to observe whether you actually bought the item, or you bought the movie, or you watched the movie, or whether you watched it for 2 minutes, or whether you watched it for 2 hours, and so on and so forth. Same thing happens with Amazon purchase as well. So one thing that Amazon also logs is how many items did you research before you actually made the purchase. So many a times you're not going to pick the first item, add to cart, and check out. You will go through like 5 or 6 items, you'll look at the reviews. After that, you will make the purchase decision. So again, Amazon is logging all of that data, how many reviews you have read, what all items you have observed, and on that basis, it gives you the recommendation, and based on that recommendation, you will check out or you may not check out. Typically, in the e-commerce business, it has been observed that people will look at 3 items and then they will make the purchase decision. So 3 items is all that you need to look at. If you look at 15 items, you will never make a purchase. You will be in decision paralysis mode. So Amazon's goal, or if you were an Amazon data scientist, your goal is to make sure that you get the decision maker, the purchaser, to 3 items as soon as possible. And you want them to check out after 3 or 4 items, because they know that if you go to 5th item or 6th item or 7th item, it's a hopeless situation for Amazon, right? So they won't make a sale, successful sale. In the case of LLMs, so you are a user, you send a prompt, you receive a response from the LLM, and then based on the response, you are either satisfied or not satisfied. So satisfied, not satisfied is a cost that is observed by, like there is a thumbs up and a thumbs down stuff, at the end of every answer. So if you do a thumbs up, then the LLM learns that you actually like the response. So the observation for the LLM is your prompt, action is the response of the LLM, and the cost is whether you give it a thumbs up or a thumbs down. Then based on that, they'll make another observation, which is whatever prompt, whatever the next question you are going to ask is, it's going to come up with a response. Based on the response, there will be a thumbs up or a thumbs down of the answer that the LLM generates. So this is all because, remember, this link is what makes something a dynamic process or not a dynamic process. You can have a lot of situations where you observe, you act, and you get a cost, right? That's an optimization problem. That's what we study in 5500. But because this action influences the next observation, that makes it a dynamic decision problem. When it becomes a dynamic decision problem, it has to be treated as a dynamic decision problem, and you have to use reinforcement learning or dynamic programming in order to solve that particular problem. And that's what is the thing that we will be studying in this particular class. So in every problem, so whatever problem you pick for a project, you must make sure that the action has to influence the future observation of the decision maker. And depending on the situation, the decision maker could be anything. It could be an LLM, it could be a a human being, it could be a recommendation system, it could be whatever, some other system. So we need to be careful about who the decision maker is. Any questions so far? Yes, please.
So for this dynamic decision process, do we assume discrete time steps or continuous time?
Very good question. So in this particular class, we will look at discrete time steps. But if you were to take this class in an aerospace department, it will be continuous time step, because rockets move in continuous time. They don't move in discrete time. But the hand wavy thing to say is that the computers are still taking actions in discrete time. So this theory can still be applied to a rocket going into space. But there is a bit of complications involved when you move from continuous time to discrete time to continuous time. But we'll not cover that complications in this class. But it's a very good observation.
And you mentioned that your research focus is continuous, the state space and action space.
Yes.
But the time is still discrete.
Time is still discrete.
Oh.
Yeah. So when a rocket is moving into space and a computer is working every 100 milliseconds, it's taking a decision every 100 milliseconds. It's a discrete time, but a continuous state problem. Okay. Any other question? Okay. So let's look at the observation. Let's look at the data center. So data center problem. What are the observations that the air conditioning system can make in a data center? How about temperature of data center, right? What else can it observe?
Power consumption.
Power consumption, very good, which is basically equal to the demand. Right. It's a very important point, because as an end user, we have a flat cost of electricity throughout the month. But if you are a commercial user of electricity, especially at the level of data center, your electricity prices are going to fluctuate throughout the day. It's going to go up and down depending on many factors in the electricity market. Anything else?
Workload.
Sorry?
Workload.
Can you say that again?
Like the category of workload of different.
The category of workload. Okay, perfect. So if you are streaming, then it's a different workload than if you're actually doing compute. You're running some complicated optimization algorithm. That's a different workload. Anything else?
The time of day,
Time of day, how does that influence?
because depending if like the data center at like 6 p.m. always gets a spike in load, you can predict that.
Okay, so forecast. Forecast of load, future load. Anything else? What else influences the energy consumption of a data center air conditioning system? Ambient temperature. Let me write it as weather, because it includes humidity as well. You want to make sure that the inside air in the data center is not too humid. Yes?
Kind of systems used, like the kind of systems used, if there are those things, the systems are old,
Right.
could generate a lot of heat.
Correct. Yeah. The kind of processors that are being used in data center. Perfect. So we have a lot of observations of a data center air conditioning system. Anything else that comes to the mind? No? Let me add a bunch of other variables. The temperature of moon. Items in Kroger. Like I've added 2 more items to the observation. Certainly we can give that information to the data center. We can feed the information about temperature on moon and the number of items in the nearest Kroger to that particular data center. And that's an observation. that becomes an observation for the data center. Based on that, it's going to act, which is just figuring out how much cold air / hot air to pump into the data center. And then there is going to be a cost accrued. How many of you are uncomfortable about giving these two information to the data center's air conditioning system? Some people are uncomfortable. Most people are not uncomfortable. You want to give this information to the data center air conditioning system. So let's think about it. The data center makes the observation. It pumps the air. It observes the cost that it has accrued in order to pump that particular amount of air. And then they get to the next observation. Did that action influence the temperature of the data center? Yes, it did. That's what we are actively changing. Does it influence the power consumption? It does. Does it influence the cost of electricity? It doesn't, right? So the cost of electricity is not influenced by this particular action of the data center's air conditioning system. Does it influence the workload? Does it influence how many people are watching Netflix at this point of time? It doesn't. Does it influence the forecasting of load? Not really. Does it influence the weather? Not at all. Weather is it's controlled by nature, not by a data center's air conditioning system. Does it influence the kind of processors that are being used in the data centers? Not really. Does it influence the temperature of moon? Not really. Does it influence the items in Kroger? Not really. Okay, so there are a bunch of observations that are not influenced by the action, right? So I can't really rule out 8 and 9 from being useless for this dynamic decision problem. But we all know that those two observations seem useless. We feel uncomfortable about putting that in the observation of the data center. I want you guys to tell me why you are uncomfortable putting those two items in the data center. You were not uncomfortable putting this in that bucket, even though they are not influenced by the action of the data center's air conditioning system. I'll wait for 1 more minute. So please think, and somebody, yeah.
Because the other ones that aren't influenced by the act influence the act, and 8 and 9
Okay.
don't react.
Okay, so his point is these things are influencing the action. All of these quantities are influencing the action, but these two may not be influencing the action of the data center's thing. So that's a good point, but that's part of the optimization problem. So whether we need to use this or not is something that should come out of the optimization, not from, you cannot enforce that this thing is useless, especially if you're in a data-driven setting. You don't know what is useless and what is not. So you have to take all the information into account and hope that the optimization will figure out what is useless and what is not useless. But it is useless. We still feel that it is useless. So why is it useless? So the reason why these two items seem useless is because it doesn't influence the cost that the data center looks at. Okay, so some of these variables, even though they are not controlled by data centers action, air conditioning action, it does influence the cost. But these two quantities, 8 and 9, does not influence the cost. Okay, so many a times, so that brings us to the definition of state in a dynamic decision process. So you can have a lot of observations, but the state is compactification of the observation in a way that the state allows you to predict the cost and to predict the next state. Okay, so I have observations I0, I1, IT. These are observations. U0, U1, UT, these are actions, and S0, ST, these are states. So I'm going to take you back to 1950s when physicists were thinking about what does a state of a system means. So state, actually, the word actually comes from a lot of studies that were done in physics back in 1800s and 1900s. So I'll leave you with this final thought. So the state is compactifying the observations and actions that you have seen so far. So what does that mean? St given S0, St minus 1, I0, It minus 1, U0 to Ut minus 1. So the state must satisfy that equation. So that's the first requirement. And the second requirement is cost at time t. T minus 1 actually. So remember we were talking about conditional probability. So this is a conditional probability, a place where we are using conditional probability explicitly. So I looked at the entire sequence of observations, entire sequence of actions, and entire sequence of state. And I want these two criteria to be satisfied by the state. Whatever we define as state of the system, it must satisfy those two criteria. So the conditional distribution over the cost, if you condition it on the entire history, it's purely a function of, it's equivalent to, it's equal to the conditional distribution on cost as a function of St minus 1 and Ut minus 1. And this number 8 and 9, it satisfies number 1, but it doesn't satisfy number 2. Okay? All of these other things, 1 to 7, it satisfies both number 1 and number 2. And that's why we were not uncomfortable with 1 to 7, but we were uncomfortable with 8 and 9. And the reason for that was because it didn't satisfy this particular criteria. You can put a lot of stuff in the state, and that's what generally happens if you are trying to solve in a brute force way. You will cram everything into the state space of the system. But if you just take a step back and you think about these two conditional probabilities, you can actually take out a lot of random stuff from the state space and make sure that your state is as compact as possible while maintaining these two requirements. Okay? So you want to have the minimal state representation of your dynamic decision process. Minimal. Okay? You can of course go even further and you can take out a lot of important stuff from the state space, but then you come up with a problem that is not solved. So many a times if you're solving something using reinforcement learning and you're not seeing any progress, it's highly likely that you have not defined the state correctly for that particular system, and therefore you won't be able to solve the problem. Yes, please.
Okay, Professor, my question is like the cost is a mapping from cost is like a mapping from the state and the action, or it's just the mapping from the state?
So we haven't given the cost as a mapping yet, because whenever you do, let's say you do a thumbs up or a thumbs down on an LLM, right? So it's not really a mapping from a prompt response pair to the action to the cost. So
if it's not a mapping, like how can we say like that?
It is still a conditional distribution. It's still a random variable. Cost is still a random variable that you observe. You see whether there is a thumbs up or a thumbs down, +1 or -1. You still see it. The only question is about the conditional distribution.
Okay.
What you are conditioning it on.
All right.
Okay. Any other question? Okay. Yeah.
Well, the lecture all be recorded and then we can view the
You can view them on YouTube for sure. If any of you have problems with the recording of the lecture, I'll just upload it to Carmen. I won't put it up on YouTube, but if you don't have any problem, I'll upload it on YouTube so that even when you are retired, you will have access to the lectures and you can go over it in your 60s and I don't know.
Will they have the access to the lecture notes?
I don't have any lecture notes, so whatever I write on the board is the lecture note. All right, thank you everyone. I'll see you on Thursday.